Oh, yeah. Good afternoon. I'm Jae Yu from Korea Electronics Technology Institute. I'm presenting Team OptimAI for solution in LPCVC track 3. We won with a server score 0.827. What is LPCVC 2026 track 3? The challenge is to detect AI-generated images entirely on a phone-grade Snapdragon NPU offline under tight latency and token limit. So it's a deployment problem, not a detection problem. Task definition. It's not just real versus fake. For each image, the model outputs a decision, A per criterion, writing, edges, texture, and so on, and natural languages evidence for each. It has to reason and explain. Two-stage inference pipeline. Our inference runs one model in two stages to using two prompts the competition provides. Stage 1 takes the image and produces free text output. Stage 2 reads that text without image and produces clean JSON. Since stage 2 has no image input, so decoding is much faster. Sample images. The organizers provide us a sample set of 50 images, 25 years, and 25 fake AI generated. The annotations hinted at which model made some of the AI generated samples. So we added some Infinity 8B and Janus Pro images to our training data, which improved our performance. Training data set. For training, we overcollect and filter hard. We use public data set like COCO, Diffusion DB, labeled by our large query vision language teacher. And we keep only the label correct in budget samples. That leaves about 32,000 images and 64,000 pairs. Constraints and scoring. On scoring, for AI images, helps the detection and helps explanation quality, and the full color of the score is just the semantic similarity of your evidence text. Push hard limit, int 8 quantization, at least 15 tokens per second TPS, and 500 tokens output budget. Explanation quality, I think the explanation quality decide the winners. Previous work, the prior edge detectors were either fast but shallow, or accurate but too slow, and base quantization broke the reasoning. We wanted both. Our approach has three pillars. Two of them, distillation and target-generated data, are the basic for this task. The third, an auxiliary classification laws, is our core contribution. Pillar 1, teacher-student distillation. A large teacher labels the data, we filter for correctness, and the small quint2VL 2 billion students learn from it. The result is near teacher explanation quality at 2 billion parameters. Pillar 2, generator-specific data. Our team sought the tests that used Infinity, 8 billion, and Janus Pro, which we had no data for. So we generated the extra images from those exact model. Only about 2% of the total data for training data set. And it lifted our score by 1.6 points. Pillar 3, auxiliary classification laws. Our students trains only on explanation text that only doesn't build a clean real versus fake boundary inside the model. So during training, we add a tiny linear classifier in the pooled hidden state with 0.05 stage 1 only. We discard it before deployment, so it's free for the device. It raised detection accuracy from 84% to 96%. That's our single biggest gain. Quantization. For deployment, we merged the LoRa weight export to ONX, the vision encoder at W8A16, the decoder at W4A16, and compared to hexagon binaries with QNN. This is the post-training quantization, and getting it to compile cleanly took several careful fixes. Debugging, yeah. What did not work? What failed? Lower validation did not mean a better server score. Overtraining, DORA, and multi-aspect, the per criterion had or made it worse. And what did work? What worked by impact, scaling, the distilled data, LoRa, the auxiliary loss, stable training, and the compiler fixes that turned a failing run into a passing one. And local server gap. Early on, validation loss couldn't predict our server score, so we built an offline estimator that it produces the server scoring formula. Even this estimator is a consistent 10 to 12% above the server score. That gap came from a small sample set, an unseen generator, and quantization rate. But the offset was consistent, so our model ranking still had. So we used the estimator to pick models, not validation loss. Altogether, we went from a 0.397 baseline to 0.827, about 108% better, and first place more than 0.1 ahead of second. The deployed model is about 2.6 gigabytes, decoding near 30 TPS token per second, twice the limit of the 15 TPS fully on the NPU. Too close. First place on our standard lesson is that a tiny and training classifier free at deployment that gave the biggest accuracy gain. Thank you. Thank you for coming, and LPCVC organizers.